In this video, I'll introduce another important model of growth, the logistic model. I'll show you the model and make connections to prior ideas from this course. Before jumping to the logistic model, I want to motivate the need for a new model by returning to the exponential model. Recall that the exponential model describes scenarios where net flow is proportional to the stock level. This is a good fit for many natural phenomena, including population growth, metabolic processes in the body, and other physical and chemical processes. But an important limitation to this model is that it doesn't take into account that there are limitations to growth that affect the stock flow system. For example, a bacteria colony does grow exponentially when given sufficient space and food. However, no matter how much food and space provided, a bacteria colony will eventually grow to fill it. This is why we don't actually have bacteria colony taking over the planet, as a quiz question predicted. The logistic model tries to take such limitations into account. We can define the logistic model by describing the net flow. Recall that the exponential model describes stock flow systems where the net flow is proportional to the stock level. For a logistic model, the net flow is dependent on two quantities: the stock level and the difference between the stock level and a carrying capacity for the system. We can express this mathematically with the following equation. Here S is the stock level, C is the carrying capacity, and K is a proportionality constant. This shows that the net flow is proportional to the product of these two quantities. This formula often gets rewritten in the following way. Notice that I factored out C to go from the first line to the second line. Then, in the third line, I renamed Kc as R. This R value is similar to the rate constant we used for exponential models. So altogether, to determine a logistic model, we need the carrying capacity C, the rate constant R, also the units for the net flow are stock units per time step, so implicitly we also need the time step T. Here are graphical representations of the logistic model. The top graph shows how the net flow depends on the stock level. The bottom graph shows, for a particular initial stock level S0, how the stock level changes over time. Looking at the formula for net flow, notice that it's 0 when S is 0 or when S is equal to C. That is, when the stock is 0 or at the carrying capacity, the net flow is 0. In the top graph, this is where the curve crosses the horizontal axis. This is also shown on the bottom graph by the leveling off near 0 and near the carrying capacity. In the top graph, we can also see that the flow is increasing for small stock levels and then decreasing as the stock level gets closer to the carrying capacity. This creates the S-shaped curve in the bottom of the graph. One additional thing to notice on these graphs is the peak flow. This is when the growth rate is greatest for the stock. On the top graph, notice that the net flow is largest when the stock level is halfway between 0 and the carrying capacity. This always occurs for logistics models and is related to properties of parabolas. Another important piece of information is when the peak flow happens. We can identify this on the bottom graph by looking at the point on the graph on the horizontal axis where the graph is steepest. On this graph, it looks like it occurs between 4.5 and 5. We'll develop ways to calculate the rate constant, the carrying capacity, and the time to peak flow in the next video.